Welcome to the West video series. My name is Enrico Remigi and I'm the process modeler in the West development team. In this video, I'm going to show you how to create a new plant layout from scratch in West and execute a dynamic simulation. For the exercise, we're going to work in the main West environment. And I've used for the exercise this standard MLE plant layout with two activated sludge tanks in series, an anoxic tank followed by an aerated tank, an internal recycle of the mixed liquor followed by a secondary clarifier. Before moving into West, I would like to summarize what I consider the typical West workflow in 7 steps. First, I will create a new project, and this can be done by either starting from scratch or by starting from a template, one of the available templates in the library. Remember that new templates can be created by end users and added to the library. I'm then going to assemble the necessary icons by dragging and dropping blocks from the block library onto the canvas and connecting them graphically. I will then go through each block and set up the relevant parameters, such as the size of the tanks, the flow rates of the pumps, temperature of the process, and so on. Most importantly, I'm going to define what is called fractionation and diffractionation models, respectively, for the influent and for the effluent, and the influent specifications. Fourth step, I'm going to create some graphical outputs like plots, tables, to view the simulation results dynamically as the simulation progresses. Fifth step, I would consider it optional. I could create some objectives, cost functions, in other words, like a performance index, for instance, which could combine effluent quality indicators, energy consumptions indicators, and so on. I will finally execute the simulation, actually 2 simulations. First, a steady state simulation to effectively initialize the system. Then the end state of the steady state will be used as initial state for the dynamic simulation. And finally, I will run the dynamic simulation. Seventh and last step, also optional to some extent, I could generate a report of the project and save it as a Word document. All right, first step, I'm going to create the new project in West. And here's the West environment. So I could do this by either selecting this option, create blank project under templates here, or by selecting the new item in the application menu. As name for the project, it's always advisable to use a meaningful name. We could call this MLE plant or something like that. This location is perfectly okay. I may also want to outline a brief description of the project. In this case, I could write nitrification, denitrification, conventional activated sludge system with controlled aeration, because I'm going to add a control loop to maintain a certain DO set point in the tanks. And I'm going to use a file, an influent file that was derived for 100 to 110,000 population equivalent. The default library is okay. As the model instance, I'm going to select the ASM1 temp. You see here there are other options that I could use. And there we go. Here's the West simulation environment with a number of panes here all around the central layout sheet, which is going to be my working area. These panes have some standard behavior that one would expect from a modern software application. They can be docked, undocked, hidden, they can be closed, left floating. I'm going to rearrange my working space in a convenient way like this, because I'm going to use the control center to launch simulations. I'm going to use block details and properties, and I'm going to use the block library to retrieve the icons that I need for my layout. One small detail, if you don't particularly like the visible grids here, like me, you can go to the view menu and click on grid lines. Now, the second step, as I shown you before, is to draw the plant layout. So by dragging the icons from the block library and connecting their terminals. So in West, I'm going to hide temporarily these panes to have more space. I'm going to take from the input and output group and a municipal wastewater. From the biological treatment, I'm going to take 2 activated sludge tanks. From the separation group, a secondary clarifier. Then again, from the input-output, an effluent pipe and a waste pipe. Then I need 2 pumps, one here to recirculate mixed liquor back to the anoxic tank. So I'll take this 2 flow splitter, and I'm also going to rotate it like this. And I need a second flow splitter, second pump in this position for the excess sludge. We'll also need a 3 combiner to collect the 2 return flows. Now, I also need to set one special property for the layout here in the properties pane insert loop breakers. I'll set it to true. And now I'm going to connect these blocks. So right click, select polyline connection, and hover over a terminal. When it gets highlighted, click and a thin line will appear. You can then drag the line to the end terminal and click again. And you do this for all the terminals. I'm going to do this very quickly like this. And here is the end result. This is the layout I wanted to get to. The next step here was to set up the plant model. And first of all, I'm going to actually rename these 2 blocks. I'm going to call this one anoxic and this other one aerated. So it will be slightly clearer, and maybe even hide labels that are not strictly necessary. Like for this combiner, I can hide the label like this. Now, to set up the influent specs and model, I'm going to double click on the municipality block. And the first page here is where I'm going to list all the available measurements that are all the measurements that I have for the influent. The list you see here is purely indicative and can be entirely customized. Let's say I have an additional measurement next to water, that is flow rate, COD, TKN, and TSS. I also have ammonia as a concentration. There we go. So I can add, very simply add a new measurement, a new component. In the second page here, fractionation, I will have to graphically set up a fractionation model. What is a fractionation model? It is an interface between the set of measurements that I have specified in the previous page and that you see here as blue blocks, and the ASM state variables that you see here in green. So I will need to define graphically this interface, this essentially a transformer between my measurements and the ASM1 state vector. I can load the base ASM1 input fractionation model layout. Yes, the message is perfectly obvious because I have added one measurement, ammonia, which is not present in my standard layout. So I can very simply, if I really want to even make it all neat, I can just move this one here. I delete the connection between TKN and ammonia because now ammonia is directly measured. I have a measurement, a time series for ammonia, so I can simply make this connection. And I could even save this layout and call it something like ASM1 plus NH4 to be used at a later stage. The third step in this influent tool is data import. Here I will read in my time series. As you can see, West can read text files as well as Excel spreadsheets. And I'm going to take this file, which I've prepared earlier. All the necessary time series are present in this file, so I can simply drag the file name down here and only complete this line, manually set the match between the header NH4 as it appears in the data file with the measurement as I specified it in the general page. The last page generating review, I simply click on generate, and this action will effectively generate the influent model, so the translation of this graphical layout, and two input files, a steady state and a dynamic influent, which will be used for the corresponding simulations, as you will see in a minute. I can do the same reverse for the effluent. Double click on the effluent block. First page will suggest a list of measurements. In this case, I can get rid of remove ammonia because ammonia is present anyway otherwise. Move the defractionation model. Here you see the reversed picture. I have in blue the state variables of the ASM1 vector, and in green the measurements that I would like to have on the effluent as I specified them in the general page. Going to load the ASM1 output layout, move to generate and click on the button. This effectively generates the model associated with this graphical layout. Good, now I can close this one as well and maybe save my project. The next step here consists in inputting the dimensions of my plant. And here's an overview of the key parameters that I'm going to set. I have to set the temperature for the two tanks, volume and aeration level in the two tanks. One will be non-aerated, as you can see here. I have to set up flow rates for the three pumps, the nitrate recirculation pump, the return activated sludge and waste activated sludge pumps, and the set point for the aeration controller that I'm going to set up in a minute. So this is an overview of the main parameters that I'm going to set in my model. Right, let's start from a temperature. The temperature is present as a parameter in both these tanks, so I can multi-select and change the temperature here in the block details and set it to 20 degrees. Then the volume of the anoxic tank is 2000 cubic meters. The volume of the aerated tank is 4000. The flow rate of the nitrate recycle, I'm going to set it to 66,000 cubic meters per day, which is approximately 3 times the average influent flow rate. I'm going to use 22,000, so 1 time the average flow rate for the sludge withdrawal pump of the clarifier, and 390 cubic meters per day, which is approximately 1.5% of the average flow rate. Now, an easy way to ensure that the oxygen level in the aerated tank is maintained at a certain concentration is to create a control loop. And this is what I'm going to do next. In the controllers group, I'm going to take the PI controller, which will receive as input the DO measurement from inside the tank and return as control action U the KLA for aeration in the tank. Now the desired oxygen concentration is to be imposed at the level of the controller. So you select the control block, and this YS, you see, set point value for the control variable, 2 milligrams per liter is fine for me now. We got to the fourth step in this West workflow, that is to prepare some graphical output to visualize the simulation results dynamically. To do so, I'm going to first insert a new sheet, see, add sheet, never mind about the name now, and add a couple of plots inside the sheet. Fast line is good. A first plot called oxygen concentration. Second plot, I'm going to plot the solids concentration in the tanks, and the effluent quality. Now, by clicking on the design mode button here in the view menu, I can slightly rearrange these plots like this. Right. It is then very easy to populate each plot by simply selecting in the layout the necessary blocks and selecting the variables that I need from the block details. So now we're looking at oxygen concentration. I have multi-selected the 2 tanks. Then I select CSO, so the concentration of dissolved oxygen, which is a variable common to the 2 tanks. Drag this one here, release, and the plot is created. Similarly, I'm going to do for the solid concentration. I'm going to select the aerated tank. XBH is the heterotrophic biomass, BA is the autotrophic biomass. Select the first one, control the second, and the TSS is the total suspended solids concentration. Drag to the sheet and release on the plot. Once more for the effluent quality. In the effluent pipe, I'm going to select NH for ammonia, NO for nitrate, total COD, TKN, and sorry, not water, TSS. Drag on the sheet, release on the plot. All right, I believe I completed this fourth step. The next one, I'm not going to cover in this video is the definition of custom objectives. And I'm going to go straight to the sixth step, that is executing the simulations. Steady state first and dynamic next. Okay, here we go. In the control center steady state page, simply click on the start button and you will see the evolution of the variables on the plots. Particularly, you will see here that the biomass in the tanks starts from 0 and grows and stabilizes around between 4.5 and 5 kilograms per cubic meter, which is okay. That the oxygen is maintained around 2 milligrams per liter. And in the effluent here, I'm just going to turn off this time series and only look at the ammonia in blue and nitrate in orange, and you will see a stable nitrification and denitrification in my system at around 40 to 45 days. Now the system has reached steady state, which can then be used as a realistic initial state for the dynamic simulation. Now, if you have this initialize simulation button enabled, like in my case, choose the option from steady state to dynamic. Otherwise, simply switch in the control center to dynamic, to the dynamic page. Set the stop time, so the length of the simulation, to 30, because I have used a 30-day time series as in the influent, and launch the simulation. You will see, for instance, that the biomass will start, the solids in the tank will start from the steady state concentration. That, although with some oscillation, the oxygen level is maintained around 2 milligrams per liter. What is also very interesting here to notice is that there seems to be some considerable biomass washout between day 6 and day 8 and between day 20 and 22. Now, if you would, for instance, quickly insert another plot, I'm also going to rearrange them nicely, sorry, like this. And the plot here, the influent flow rate, you will remark that the biomass washout, I need to rerun the dynamic simulation, is caused by two intense rain events, exactly between day 6 and 8 and days 20, 22. Very well, so we've executed the simulations, and now the last step is to generate a report. I just would want to show you how to do this, because I believe it's a very cool feature of WES 2016. Now you go here in the project menu, reports, and simply select the individual elements, items of the project that you would like to export in your report, in the Word document. I have selected here the general information, which is the description I've entered when I created the project, and that, by the way, can be maintained as you work through the project from this general button here. I've included the layout, of course, and my output sheets. Then I can click on preview to visualize the preview, and then I can save it as Word document. Where is it? This one here, docs. That's it. Okay. And this is really all for this video. I thank you for taking the time to watch, and please come back for more. Goodbye.